What is up, guys? Welcome to another episode of CCT, and today we're going to continue with this everyday easy problem series. This is a problem that I think I've done before. Let's see. Yep, 3 months ago. Interesting. Okay, but I don't remember how you do it, and we're going to do it again, and you're going to see me doing it live. Alright, so let's jump right into it. Let's open up the board. And the color, let's do orange. Or no, let's go hot pink red. I'm feeling hot pink today. Or this color. Okay, yeah, that's cool. Alright, so basically inverting the tree. So just by looking at this example, it seems like you swap these, so 2 and 7, you swap the left and right basically. It becomes 7 and 2. But then again, so the left of 7 is now 6, but now it's 9. And the right of 7 was 9, but now it's 6. So like every single left and right was swapped. That's what inverting means. Okay. So let's just draw some things out. 7. Do 1, 2, 3. So what I'm doing a binary tree problem like this, something that definitely jumps out to me is using some kind of recursion and doing something on the left and right. Like, for example, doing one step to swap the left and right of this level, and then after I do that, I say that like 1 gets the inverted, or so like root's left now gets the inverted of root right. And that would be if my recursive call was like inverted and it returns a node. So like I want the left side to not only get the right node, so like I not only want it to get 3 and 2, but I want it to be the 3's inverted tree. I want this whole thing to be inverted, and I could do this with a recursive leap of faith. Like just say, okay, just give me the inverted right side, and then I'll just link up the root left to it. The root left is going to get this inverted right side. And I like to call it a leap of faith because like let's worry about actually getting this part to do it later. But let's just imagine that we can get this inverted right side. Okay, so let's build up more on this idea. I'm gonna start over here. So I'll just call it im, and I know it's gonna return a tree node pointer. And I know it's also gonna take in a tree node pointer. We'll just call it root. Whoops. Okay, and whenever I have binary trees, I always have to do something to the left and right side. So I do really like this idea. Yeah, I like this idea where I do something root And this is how I usually start binary tree things. Or binary tree recursive functions. I'll call this step 2. We'll have, I think, 2 steps. And this is when step 2 is when you do something to the right and left side. So this is going to get in of root right. And then, well, you guessed it, the right side is going to get the inverse of the left side of the tree. Left. And also step 3 is you have to figure out what are you going to return. What do you need this left side to get? Because this is inv. What do we want it to return? Well, we want it to return the root after it's inversed both the left and right side and swapped those two. So this inverted this part of the tree, or this part of the tree, and this part of the tree, and then swapped the left and rights there so that it looks like this. So now that that's all done, we've inverted this part of the tree, and let's return the root. Okay, so then that leaves us with our base case, which is the first thing. I like to do it in this order though, like 2 first, figuring out the meat of the problem before I get to the ending case or base case, whatever you call it. So let's see. When do we want to stop? We want to stop when it's null. Well, yeah, let's just keep it simple. Let's just stop there. So if not root return, I mean the root is null pointer. We could have just returned the root, but whatever. So yeah, let's actually try this out. Over here maybe. Whoops, no. Oh, there. Let's try this out. So we got 1, 2, 3, 4, 5, 6, 7. Okay, first call is the inverse is with the 1 as the root. The 1 is not a null pointer. So root left, which is pointing to 2, gets the inverse of root right. So it's getting the inverse of whatever the inv of 3 is gonna. Yeah, so the left side just is getting the inverse of the 3, and the right side just, or actually, wait, we're going through this as a stack. So then it goes into here, and so remember we're at this, and whatever it returns, the 1's left pointer is going to point to it. But we're here. This is what the root is now. So no, it is not a null pointer. Here then we get the root left. So the root left of 3, so actually let's blow this up here. So the left pointer of 3, which is here, is going to get the inverse of the right side of the tree. Okay, so now we're going into the stack of 7, and 7 has null and null. So 7 is not null pointer itself, but if you go into the left side, it is going to be null. So sorry, it actually, if you go to the right side, because we're looking at the root right, that's null pointer, so that's going to return null, and that returned. So root left gets what was here, which is null, so that's good. Ooh, wait a second. Well, I guess this isn't so important now, but like the left side has changed at this point. Because now like it'll still be null here because they were the same thing, but anyway, let's pop back up the stack. So basically now we're back here with this being the root, and root left is comfortable to get this. So now it's become 3, 7, 7, and the problem here is that when we're now taking the right side and making it the inverse of the left has already been modified. So what we need is a way to store the actual left part. So I think we could just do temp gets root left. Yeah. So then when it's overwritten, we still, and then this just becomes temp. So now if we continue, so then it's saying the right side gets the inverse of temp. What is temp? Temp equals 6 null null, and we know the inverse of that is just going to be 6. So then this has finally returned 3, 7, 6. By the time it gets to here, it's going to return the 3. Okay, so now we jump back to when 1 is the root, because the left side of this, wow, this is getting messy. Let's erase. Oh, we ran. Dang it. That's not a good way to erase. Whatever. Wait, could I just get a bigger... Okay, anyway, now we have 1 is pointing to 3, 7, 6, because we're on this now, and the right side is also pointing to 3, actually, yes, 7, 6, because those were swapped, actually. Okay, but now the right side is going to get the temp of left, and temp of, or the inverse of temp of left. Temp of left is this, so 2, 4, 5, and then the inverse of this is going to return 2, 5, 4, and then the 2 is going to return, and then the right side is going to get 2, 5, 4. Alright, let's code this. So base case is if your root is a null pointer, just return the root. Next, let's get a tree node pointer for, and I mean this makes sense, like simple swapping, you always need a temp, right? So tree node temp gets the whole root left side. Then let's actually modify the tree node left side now that we stored it. Whoops. Root left can get the invert tree of root right, and then root right can get the invert tree, and root left has already been modified, so what we need is the temp of temp. Then we just return the root. Okay, cool. We got that part right. Let's think of base. If the root is null, that's fine because it returns there. What if it's like a stick? Yeah, that should be fine also because it just returns early, like, and then it just gets the other side of it. Yeah, I think this should be good. Nice. Alright guys, I hope you enjoyed this CCT video. That was cool to see that my original thought wasn't right, and only until I like traced it out did I figure out that, oh wait, when you swap things you need a temp. So things to take out of this, just to recap: binary search problems, I think this 1, 2, 3 formula, not saying it's ever easy to do these things, but because each one of these parts is hard to come up with. But I think this formula is pretty sound. You have a base case that you like have to return at some ending value, and when it's null, that's oftentimes the answer. Number 2 is that you should do something to the left and right side because it's binary. And number 3, you need to know what to return, and you have to think of that part in terms of what did you need this root left to get out of this function. Did you need it to get a number, an integer, a root? If you're reconstructing the tree, you need to return some kind of node, basically. That's another key point. Yeah, so I hope you learned something from watching me go through this live, and if you have any other questions you want me to go through or any concepts, just let me know in the comments and I'll be sure to do that. Alright, thanks. See ya.